Hello, chemists. This is Ms. Placino, and you are watching Screencast 5.3 on balancing chemical equations. This lesson is really a crucial one, as balanced chemical equations are going to play a substantial role in nearly everything else we talk about. So we're going to talk about how to balance chemical equations for mass. Let's take a look at the do now. Early alchemists tried to turn lead into gold. Why weren't they successful? Chances are you've heard of alchemists before you came to chemistry class, and you knew that they're trying to take metals that are of not a whole lot of value, something like lead, and turn it into something very, very valuable like gold. So alchemists tried all sorts of chemical changes, trying to take cheap metals and turn them into gold. And despite all of their best efforts, they were never successful. The reason for this, and hopefully you figured it out from the reading, is if you don't start with gold as you begin a chemical change, there's no way you're going to produce it at the end of a chemical change. A chemical change is just going to take the atoms that are present, let's kind of make a little molecule that's just supposed to represent something very generic, and as a reaction occurs, you can do things to change the way the atoms are bonded together to create new molecules, but you can't create new atoms or new elements. That's more of a nuclear change, and alchemists definitely did not have access to that sort of technology when they were doing their work. So if it's not on the reactant side, there's no way an element can be on the product side. All right, let's get into today's lesson. Let's start off with some signs of a chemical reaction. Hopefully what catches your attention when you look at this picture is that light is being given off. Oftentimes the evolution of light and or heat is signs that a chemical change has occurred. You can think about your Bunsen burner in lab. When you take methane, CH4, and you react it with oxygen, O2, you're going to produce a lot of light and heat. Many times a color change is signaling that some sort of chemical change has occurred. In the beaker with the clear solution, we have an acidic solution. An indicator is present in there called phenolphthalein, which is able to change colors as the solution changes pH. So if I keep adding a base into my acidic solution, maybe it'd be better off if I did it this way. Acid down here, we're going to add a base. The two will react. And then eventually we're going to change the pH enough where the indicator has changed color. Another sign of a chemical reaction is the formation of a gas that's going to bubble. It wasn't that long ago that we were in lab and you reacted zinc with, I think it was, let's get rid of that, H2SO4. And one of the products you made was hydrogen gas along with zinc sulfates. And those bubbles were telling you that a chemical reaction was occurring. And finally, let's erase this. The production of a precipitate is another good signal that a chemical reaction is occurring. Here we have two aqueous solutions, so things that are just dissolved in water to form a mixture, and it looks perfectly clear. However, when I mix them together, it looks like I'm starting to form this like yellow cloud. In reality, that is a yellow solid, and if you give it enough time, it's going to settle to the bottom of the beaker, and it'll be very clear to see that it is a solid. So these are four signs that usually are indicating that a chemical change or a chemical reaction is occurring. We're going to represent chemical reactions with equations. We've got numbers in front of different species. In this case, the 2 in front of H2 is what we call a coefficient. Same thing as the 2 in front of H2O. And then in parentheses, a lot of times you'll see that should be the letter L. I know it's kind of tough to tell there. This is the G, that's a G, and that's representative of the phase of matter. Sometimes when we're writing equations, we'll tend to leave out the phase of matter, as many times it's kind of implied. If you're talking about hydrogen and oxygen, there's a really good chance you're talking about gases. Everything to the left of the reaction arrow is called the reactants. And these are going to be the materials that enter a reaction. These are our starting materials. The coefficients are telling us the ratio. You can think of it for the time being as, okay, I need 2 molecules of hydrogen to react with 1 molecule of oxygen, and then I'll produce 2 moles of water. Water is an example of a product. It is the material that exits a reaction, so it's going to be on the right side of the reaction arrow. So just to clean this up a little bit, let's get that out of the way. Collectively, everything to the left of the reaction arrow are called the reactants. Everything to the right of the reaction arrow are called the products. Before we move into any more real detail about the equations, I want to talk a little bit more about the phase of matter. There is something that we have, hopefully we know that S is for solid, G is for gas, L is for liquid, but a lot of times you're going to see AQ, and AQ stands for aqueous, and all aqueous means is dissolved in water to form a solution. So I can take a solid, in this case I've got copper sulfate pentahydrate, I can dissolve it in water, and if I stir it long enough, I can create a homogeneous mixture. So you can see that I don't have a solid in there anymore. I've got this blue solution, and we'll talk more about this, but in reality, you have Cu2 plus ions floating around. You have SO4 2 minus ions floating around. And then you have lots and lots of water molecules as the liquid medium. So this is how you'd make an aqueous solution, and a lot of the reactions that we run at this level of chemistry take place as an aqueous medium, as they tend to react faster than something like a solid. When we're balancing chemical equations, what we're really trying to do is apply the law of conservation of matter. The law of conservation of matter states that matter cannot be created or destroyed. It can only change forms. Really what this means is when I go to balance an equation, I need to make sure that there are the same number and same type of atoms on both sides of the equation. It's not possible for me to get rid of an atom or to create a new one. Matter cannot be created or destroyed, but it is possible for me to break the bonds of the reactant molecules, rearrange the atoms, rebond them, and form new molecules. That's what we mean when we say that matter can change forms. It turns out that not only mass, but also energy and charge, they're all conserved in a chemical reaction. We'll be talking more about the conservation of energy in a reaction when we talk about thermochemistry, probably in February, and charge we'll deal with in May when we talk about redox chem. But for the time being, just know that all of those are conserved. It's kind of an infamous Regents question, which of the following are conserved in a chemical reaction? It's all three. We have to balance for mass, for charge, and for energy. So let's go ahead and try to balance a chemical equation. As reactants, we have Sb, which is antimony, and we have oxygen, O2, and our product in this case is Sb4O6. First thing you want to do is kind of size up the equation and see what you're working with. So I'm going to count the number of atoms of each element on both sides of the equation. Well, on the reactant side, I have 1 antimony, and I have 2 oxygen atoms. On the product side, I have 4 antimonies, and I have 6 oxygens. So hopefully right off the bat, it's very, very obvious that this is not balanced. In order to balance the atoms, you need to add coefficients. You cannot change the chemical formulas. In other words, you can't change the subscripts. It's not okay for you to just do this. Get rid of those. This is kind of annoying. Let's just make that Sb1O2. Now it's balanced. Well, no, you've completely changed the product, and you don't know if SbO2 really exists or not. You have to leave the subscripts alone. So what you want to do is kind of go back and forth. It's almost, well, they say it's balancing by inspection. You can think about it as guess and check. I have 1 antimony atom on my reactant side. I have 4 on my product side. I can quickly balance these by putting a 4 in as a coefficient. If I go back over to my product side, I've got 6 oxygen, only 2 on the reactant side. I know that I can get to 6 if I put a coefficient of 3 in front of O2. 3 times 2 gives me 6. There we go. I've got 6 oxygens over there. You don't have to write a coefficient of 1, but a lot of times I do, just to remind myself that I've already done this problem and I balanced the equation. And they have 4 antimony plus 3 O2 molecules will yield 1 antimony, or I should say Sb4O6. Now, let's not do that just yet. So let's go ahead and look at some practice problems. All right, so if you look at your workbook, you'll see that you have 40 balancing practice problems. You might have noticed that kind of the theme of this unit is repetition. It just takes a lot of practice to get comfortable with things like naming and balancing. I'm going to just focus in on like the first four. And for the time being, don't worry about what these other lines are for. We're going to use them to classify these reactions, something we'll talk more about in future lessons. All right, so let's talk about 1 through 4. Question number 1 is really similar to the practice problem that we did. We've just got the 2 elements, 2 reactants, and 1 product. So I see N2 plus O2 makes N2O. I've got 2 nitrogen atoms as a reactant and 2 nitrogen atoms as a product. So this is not a good place to start because it already appears to be balanced. So that means I'm going to have to look at oxygen. I've got 2 oxygen atoms on the reactant side. I only have 1 on the product side. In order to fix that, I'll put a coefficient of 2 in front of dinitrogen monoxide, N2O. That's going to unbalance my nitrogen. I now have 2 times 2, or 4 nitrogen on the product side. I still only have 2 on the reactant side. So if I put a coefficient of 2 in front of N2, that will balance for nitrogen. I don't need to put a coefficient in front of O2. There are already 2 oxygens on both sides, so I'm just going to put a coefficient of 1 in front of the O2. If we take a look at question number 2, we have Bn plus F2 yields Bf3 plus N2. So this is a little bit more complicated. We have 3 different elements that we have to keep track of. I've got 1 boron on each side of the equation, so we don't really want to start there. I've got 1 nitrogen and 2 nitrogens, so we're not balanced for nitrogen. And I see 2 fluorine atoms and 3 fluorine atoms on my product side, so I'm not balanced for fluorine. Let's go ahead and start with fluorine. If I've got 2 on the reactant side and 3 on the product side, we can look for the least common multiple or lowest common multiple. Between 2 and 3, it's 6. So in order to get to 6 fluorine atoms, I'd have to put a coefficient of 3 in front of F2. That gives me 6 fluorines on the reactant side because 3 times 2 is 6. I can put a coefficient of 2 in front of boron trifluoride, Bf3, because again, 2 times 3 gives me 6 fluorines. Now that has caused my borons to no longer be balanced. I've got 2 borons on the product side. I only have 1 boron on the reactant side. I can clear that up by putting a 2 in front of Bn. Now I've got 2 borons on both sides of the equation. Let's check nitrogen. I've got 2 nitrogens on the reactant side. Oh, I've got 2 on the product side. So this is completely balanced. Question number 3 is where things can start to get really complicated with balancing. So let's clear this up a little bit. All right, so in this case we have what's called a double replacement reaction, and we've got 2 compounds on both sides of the equation. One trick that you can use to help make things a little bit easier is looking for polyatomics. We have sulfate on the reactant side, and we have SO4 sulfate again on the product side. We have hydroxide, OH, on the reactant side, and again on the product side. So instead of treating sulfate as a sulfur and 4 oxygens, treat sulfate as one single unit. It's not incorrect to balance them as a sulfur and 4 oxygens, but it's probably going to make your life a lot easier to treat it as a sulfate instead of as individual atoms. Let's take a look at this question. We're very clearly not balanced. I'm not going to go through the way I did with questions 1 and 2. Basically, you need to pick either iron, sulfate, potassium, or hydroxide and start balancing. I'm going to pick, I'm going to go with iron to start with. I can see that I've got 2 irons on the reactant side. Over on the product side, I only have 1. Let's fix that with a coefficient of 2. Now there are 2 irons on both sides of the equation. The next logical thing would be to check out my hydroxide, since I just made a change there. I've got 2 times 3, or 6 hydroxides on the product side of the equation. If I go back over to the reactant side, I only see 1. I can fix that by putting a 6 in front of KOH, potassium hydroxides, and now I'm balanced for hydroxides. The next logical place to go would be to look at potassium. I've got 6 potassium on my reactant side. 6 times 1 is 6. I only have 2 on my product side. If I put a coefficient of 3 in front of potassium sulfate, I can get 6 potassium atoms. Finally, if I take a look at sulfate, I have SO4, no subscripts there, but a coefficient of 3, so I have 3 sulfates. And if I look over at the reactant side, oh, how convenient, I have 3 sulfates there. So I could balance by putting a 1 in front of iron 3 sulfates. It's just really how you kind of have to do questions like this. Pick a spot to start, pick an element or a polyatomic ion, and kind of just go back and forth from reactant side, products over to reactants, getting things balanced. If it doesn't work out, you can always just erase it and start over. All right, the last one we're going to talk about is taking H3PO4, hydrogen phosphate, and then we've got it turning into H4P2O7 and H2O. All right, so this one looks pretty complicated. Let's see if we can figure it out. We've got H3PO4. I'm going to start with phosphorus because phosphorus just shows up once on both sides of the equation. Hydrogen and oxygen show up in multiple spots on the products, so that might make them harder to deal with. So I've got 2 phosphorus atoms on the product side. In order to get 2 on the reactants, I'll put a coefficient of 2 in front of H3PO4. Let's see what that does to, we'll go with hydrogens first. 2 times 3 is 6 hydrogens. I've got 4 hydrogens from the first product plus 2. That gives me 6 hydrogens altogether. So I'm balanced for hydrogen. Hopefully that's the case for oxygen as well. 2 times 4 gives me 8 oxygens on the reactant side. I've got 7 plus 1, which equals 8 oxygens on the product side. So I can just put coefficients of 1 in front of both of the products. I said it before, I'll repeat myself. Balancing, much like naming, is something that requires a lot of practice. There's a reason you have many, many practice problems to play around with. It's because you need to get that repetition in. So my recommendation would be to tackle a bunch of these practice problems, make sure that you're checking your answers against the answer key online, and just get comfortable with it. This is something that needs to kind of be second nature as we move forward. So that's it for today's lesson. I hope you found it helpful, and thanks for tuning in.